Welcome to May's Leetcode Challenge. Today's problem is n queens 2. The n queens puzzle is the problem of placing n queens on an n times n chessboard such that no two queens can attack each other. Given an integer n, return the number of distinct solutions to the n queens puzzle. So we've seen this problem before with n queens. N queens 2 is actually a little bit easier because we don't need to return the solution itself. We're just going to return the number of solutions. So really, we could do the same approach here. We'll have a backtracking solution using a depth first search recursion. What we'll do is start at every single row, select some cell, pass in a set of all the other cells that are now prohibited, and now go down to this next level and try every single cell that's not prohibited and try to continue this depth first search. If we're able to get to the row of n, that means that we found a solution that will increment our output by 1 and just basically find every single combination that we can, but it's going to be a little bit optimized because we're not going to continue any further if we find that this cell is prohibited. Okay, so let's begin by first initializing our output to be equal to 0. At the very end, we're going to return this self output. Now the key thing here is to write our depth first search, right? So depth first search, what do we pass in? We're going to pass in the row, okay, because that's going to tell us whether we've completed the solution or not. And we're going to pass in a set of all the prohibited cells. So I'm just going to call this X as for excluded. So first thing is if row is less than n, then we want to continue this depth first search. Otherwise, if it's not, we can just increment our output by 1. And then we'll end our recursion. Now here, let's see, we're going to have to do it for every single column, for a column in range of n. We want to check to see first, is this row column excluded? Because if it is, then we just stop immediately. We can just continue and then go to the next column. So if row column is in the excluded, then we just continue. That was simple. Now, otherwise, we are going to first create a subset of all the excluded columns underneath this row column here that we're trying to calculate. So there's going to be 3 conditions, right? All the columns underneath this cell, all the columns to the diagonal right, and all the columns to the diagonal left, or not columns, cells to the diagonal right and left. So to do that, I'm just going to kind of brute force it here and say row 2, row 3 equals row 3. All of these are going to equal to row, and we'll keep track of all the columns as well. These are all equal to column. So the first thing is all the cells underneath, we want to add that. So while R1 is less than n, we are going to add to our X sub a tuple of, let's see, row 1 and column 1. And each time we're going to, well, we're going to start off by increasing the row 1 here. And that should be it for the columns underneath. Now the columns to the diagonal, or cells to the diagonal right, I'm going to say while, I mean, we know it's not going to like flip around. We just want to go all the way to the end column here. So this would be column 2, while column 2 is less than n. First going to increase our column by 1 and increase our row by 1. We'll add that to our sub-excluded set, R2, C2. Finally, we want to do to the diagonal left, while C3 is greater than 0, because that's the last column that we could, column cell that we can add. First, we're going to decrease our column by 1 and increase our row by 1. We're going to add this to our X sub, R3, C3. Finally, make sure to call our depth first search, but we're going to add 1 to our row, and we'll pass in the X as well as the OR operator to basically combine these two sets, because it's going to build, right? The more rows we go down, the more cells that become excluded. So we'll do an X, we'll do an OR X sub, and that's it. That's going to be our algorithm. Now all we need to do is call this depth first search. Call our depth first search, pass in row 0 at first with an empty set. And that would be it. So let's see if this works. Okay, I always make that mistake here. Has to be a tuple. Okay, that looks like it's working, so let's submit it. There we go, accepted. So you can imagine if you visualize this, we start at this cell here, then we're going to like create a prohibited cells, like all these aren't available, all these aren't available, and then we'll continue to the next row, and we'll start with like here, okay, that's excluded, this is excluded, oh, we can do here though, and then we'll continue on. And if we can't get to the last row, then it's just going to backtrack all the way down. So basically every single combination that should be possible is going to be tried. So that means time complexity is going to be n factorial. Same with space complexity. Now you could optimize. I used a set here. You can use bitwise to save some space and some a little bit of time complexity as well, because you don't need to. You'll be building up every single row. But I found that a little bit hard to understand, even though it was pretty clever. So I didn't go with that solution. But if you're familiar with bitwise and want to try that out, I definitely recommend it. Okay, thanks for watching my channel. Remember, do not trust me. I know nothing.